cumulative noise. Cumulative observation process. We're going to call this ST as observation process. And this is really the cumulative observation process. It's a cumulative observation process. So keeping in view the definition of it, so what would be the dynamics of this cumulative observation process? The dynamics of the cumulative observation process is going to be the actual process plus, beta of t and this white noise. Maybe, so if it is dt, so let's call it, what do you call it? If this guy is, if I call this b of t, something silly. Okay. This process has a randomness. Okay, so that's another noise. While this guy is a different noise. Okay, so let's assume that these two noises are independent of each other actually. So let's, and let's assume that I denote this noise by not beta of twt but beta t dot actually. Okay, dbt by dt. So that's another Brownian motion. Okay, independent of the previous one. So it's not normal for two noises. So this was a random piece of information, and more randomness is added into it. So let's call this dBT, if you're going to write it in this manner. Okay. So what is the filtering problem actually? Central filtering problem. So precise statement of it. Precise statement of this goes like this. Okay. So imagine you have these given cumulative observations where up to the time t. Okay. And this Q satisfies the, this is star. So given you have these observations satisfying star. Okay. So what we need to do, we would like to find the best estimator. Really the best estimator. Let's call this best estimator by anxiety hat actually. Okay? Of anxiety. The state anxiety actually. Take it. So one of such best estimator is this function R of t, which is called the and the R of t is the expectation of xi t square minus xi t. Okay? So what would be the best estimator? The best estimator would be that estimator. The best estimator is going to be a process that minimizes this root mean error actually. Okay? That minimizes R of t.
So isn't it same we did in the function?
Okay.
We are taking two elements from L to omega and this is the norm of
Yes,
L.
that's an L2 norm. So in other words, that you are asking which of the anxiety head is going to give me the minimum value of this. Okay. And we did some kind of a results, similar kind of results, but deterministic results in function analysis actually. Okay. Where you are trying to minimize the distance between. So you had a fixed element in Hilbert space, and then you want to find what you call the best estimator of that actually. Anyway. So let me write the theorem that answers this actually. Not getting into the proof of it, if you want to see the proof of this theorem, you need to go to the Brent. Okay. So I'm going to do what? I'm going to write that theorem and maybe do one example based on it. So here's a precise statement of theorem. There is another thing. It turns out that this best estimator that you are interested in, this anxiety head, it's really the conditional expectation. Okay? It's the conditional expectation of this anxiety given
F tilde D.
what do you call Ft. So you may assume Ft to be the filtration that is generated by filtration that is generated by St or Qt. Okay. It's the filtration generated by St, but St and Qt is something in the terms of St, so this it's same as the filtration generated by St actually. So in other words, you need to find this conditional expectation. So this opens a lot of doors actually. So what you can do, I know that conditional expectations can be seen as a solution to a PDE actually. So one thing could be that, can we find that PDE whose solution is this and it can give us the best estimator. But there are many things that conditional expectations can do in data actually. You have this famous HGB equations, Heath-Jarrell, Heath-Jarrell-Bolton or Boltzmann equation. So it's an entire area, it's not a, one can teach a 2-semester course on stochastic filtering actually, so it's a huge area. Okay, I'm not an expert in that actually. Anyway, so here's a theorem. But it's an interesting area. That's called the Kalman-Bucy filter. See, most of these things you might find that they are very theoretical, but their implementation is easy. It's not difficult. The real thing is making yourself convincing yourself that why this algorithm works actually. But the implementation is not a big deal actually. So Kalman-Bucy filter. So here's the thing. Imagine I have this state of a process anxiety. So this observed process that satisfies this d anxiety a of t. I mean, it's written in book. I mean, if you wish, you can write it. Otherwise, just see. Plus beta of t dwt, okay, and AB are deterministic, A and B are deterministic, okay, and what? As I said, let's assume that omega naught and the Brownian motion are independent of each other. Okay. Now let's assume that this initial state of this of the process, this is a random variable actually, has a mean mu, and the variance of this xi naught is sigma square. Okay. So I have an input process that has this precise description actually. The input process. Okay. And then let's assume we have this observation process. So this was input. Assume that the observation process is this qt, qs, where s is between 0 to t. Okay, and it satisfies this ODE dqt. Okay, alpha of t, xi of t plus beta of t and dwt. D dt. Okay, where alpha and beta are deterministic and bt is independent of Brownian motion wt and obviously xi as well. Then, as I said, the best estimator that can minimize this error is this conditional expectation. Question: how to find this conditional expectation? Answer: you can find this conditional expectation by solving a stochastic differential equation. Okay? Then this best estimator xi d tilde of obviously input process xi t satisfies the following SDE, that d xi t hat is u of t xi t hat plus v of t dq, where xi naught, if this is really the best estimator, should have the same mean as xi naught actually t, where xi naught is really this mu. Okay? So the question is, what are u's and v's actually? Where u and v are this. So v of t is this alpha of t, beta square of t, r of t, and u of t is a of t minus what? Minus alpha over beta of t square, okay, r of t. Is that making sense? So the u's and v's. So you see, I can determine u and v from really, if I know the, so if I know the input process, maybe the deterministic function that deals with it. Obviously, don't know the input process. That's what we would like to find. Okay. But if you have an estimation for this a's and b's, and you know this observed process, in other words, these coefficients, you can compute this u and v. Alright. The only thing would be, what would be this r? So this r satisfies the Riccati equation. It's a solution to Riccati equation. So what's it? Where r of t satisfies this Riccati equation. I hope you have done it in your ODE course actually. It's really the first chapter when you solve the first order ODEs actually. I mean, if you haven't done it, you can open the book and read it, and it's a straightforward kind of equation. Okay. So it's dr by dt. Okay. So it's really the equality equation is where the dr by dt is equal to a polynomial in R of t, a quadratic polynomial in R of t. So, okay. So p square of t plus 2 a of t r of t minus alpha square of t over beta square of t and r square of t. Okay. So it's a quadratic polynomial in R with variable coefficients. Okay. So you also know the a and b. So
what is doing there? I mean,
I'm sorry.
In this stochastic process,
Uh-huh.
stochastic theory, what is this ODE doing?
Which is this ODE?
Arithmetic.
Okay, so here's the thing. Now, the issue is that this is a theorem. Okay, so when it was proved that you have this input process, you want to observe this process, and you want to find the best estimator, then the best estimator satisfies this SDE. So that's really the pivotal argument, that the best estimator satisfies this SDE. Now, if you want to find best estimator, you need to solve this SDE actually. Okay? Numerically, whatever. And in this SDE, you have U and V coefficients. So it turns out that for computing U's and V's, so the U and V depends on alpha beta, in other words, your input process, and the R of t, okay, the process that satisfies this stochastic, this simple deterministic differential equation. So if you know this, you know your SDE, and you know the best estimate. That simple is it. Okay. Obviously, the more dynamics will be unfolded when you get into the proof of it, that why you have this equation the way it is actually. Obviously, it's like, you know, you took this linear SDE with the linear drift and linear diffusion, and we kind of showed that its expectation and variance satisfies a differential equation actually. So if you want to find, for example, the expectation variance of a SDE with a linear drift and linear diffusion, you need to solve this differential equation. So maybe something like similar happens here and find it. Okay. So it's really self-explanatory. For example, I can give you. I mean, if you see in book, it gives multiple examples. Okay. So I'm just, and you can have a look on, for example, in one example, it gives that imagine we would like to have observe the blood cholesterol of a, for example, a normal person actually, someone taken, and that cholesterol level. So it's example 11.9.4 actually, 11.9.4. Okay. So you have this blood cholesterol of level that denotes by CT, okay, and it satisfies the SDE. So this observed blood cholesterol, okay, satisfies an SDE, and it turns out to make more sense actually, because all these, most of these lab reports are approximate actually. They are not really, okay, but imagine that the tools or the machines that they are using are equipped with such kind of filters actually, which can not only observe the original, data, okay, but they also realize that there can be noise in this data actually, and how to reduce it actually. Okay. So in many of such situations, there are such filters working. I don't know about the labs that are working here, that whether they have maybe the Arfan or something like that. The big ones actually have kind of a technology in which they not only observe what they want to observe, but they want to make sure that they have a correct observation of things actually. Okay? So the cholesterol level, you observe it. Like a few days back, I checked my cholesterol level, everything okay. So they said we can have some more, funny foods. But now, if I rely on them, the trouble would be that their results are noisy. So the cholesterol level that we observe contains the bit of, for example, noise. Okay, so it gives a stochastic differential equation. Then it, develops, what do you call this? Observed differential equation. Then it's, computes this u's and v's and solve this Riccati equation. And once you have this Riccati equation, it gets this u's and v's and then solves this SDE and then come up with the estimate of the cholesterol level actually. Okay, the best fit cholesterol level to the